I will speak to you about some a bit more lightweight aspect of the school, just about surveys and observations a bit in a historical context. Because you will hear and you have heard already about many different aspects of cosmology and large-scale structure in other lectures, so I thought that I will start with something that is a bit more lightweight. You probably have seen this famous picture in your textbooks or your lectures, how the large-scale structure of the universe looks observationally. These are, of course, just some chunks of the sky, so-called cone plots from CFA2 survey from the 80s and Sloan survey from early 21st century. And you have heard already about the cosmic web, the first lecture by Professor van der Weijert. So there are these filaments and voids and all these structures. And generally, as I believe you know already as well, we usually break down the cosmic web into this network of filament walls and voids around them. And this cosmic web is really visible both at redshift 0, so basically in the local universe, if you project galaxy distribution of the sky, even if you don't know anything about the distances. Of course, this is some catalog limited to some distance, but still you see, for instance, this is the supergalactic plane here, the Shapley supercluster, this Perseus spices. And also this cosmic web, this large structure was visible already if you go to redshift of 1 or even more. This is a plot from very successful survey Vipers, where also you see some already hints of walls and other structures. And if you think about some bigger picture, this is of course not a real observational picture, but some composition from observations and simulations. But if you think about the whole observable universe, a rough estimate gives that there should be some 10 to 11 galaxies. Although some people say that the new results from James Webb may revise these numbers because we don't really know how many galaxies there were at different redshifts. This is still up to study. And each of these galaxies, on average, let's say, has 10 to 11 stars. So these are really the numbers that we are confronted with. And if you generally think of types of galaxy surveys that measure this large structure, so there will be starting from low redshift wide-angle surveys which try to cover even the full sky, or at least the full sky available from a given place on the ground, like 6DF, which cover the whole southern sky up to redshift 0.05, say. Then you go progressively to deeper surveys covering a bit less of the sky, and like SDSS, DF. And then you have these surveys which try to mix the two, that they try to cover smaller chunks of the sky but go deeper, like Gamma did. And finally, there are lots of surveys which are sometimes called pencil beam because they look at small chunk of the sky but go very deep, like the Cosmos, which will extend much towards this plot. And of course, on this plot, we are here in the center. Yes, these are one of the celestial coordinates. The other is collapsed. And if you look into some other pictures from, for instance, 2DF Galaxy Survey Plus Quasar Survey, which was made with the same telescope, there is the more local structure of galaxies, and then quasar. These holes here in between are because of the observing strategy. Just this 2QZ survey covers just some parts of the sky. And finally, which I think there will be covered by the end of the school, there are simulations which tell us that basically the structure that we observe is really well reproduced in simulations, and this is one of the great successes of cosmology, that we can run computer simulations which are really reproducing what we observe in surveys. But why do we need those surveys? because, for instance, if you think of results from the Planck mission, the cosmic microwave background, basically Planck, almost on its own, can tell us most of the details of the cosmological model, and that's it. And what we need just like this. Well, first of all, before we had such great CMB experiments as Planck, the surveys were already there. So that's one of the reasons why they were needed. But secondly, you cannot really constrain all the parameters with just CMB alone. And finally, if you start seeing some tension between what CMB gives you and surveys give you, then this is a hint that you really need to go look closer. And what surveys gives you is that because the distribution of galaxies you can observe from really redshift almost zero up to higher redshifts, so this is a very different stage of the universe that CMB gives you. Although, of course, CMB also the photons interact with matter. You will hear about this in John Peacock's lectures, for instance, and they also tell you something about the local galaxy structure. But in general, if you want to study the universe at different redshifts, the cosmic web and the galaxy structure is one of the great tools for that, because the distribution results from different physical processes we understand quite well, gravitational instability, starting really soon after the Big Bang, when after recombination until now, the collapse and in the dark matter galaxies are formed. And we can study various statistical properties of the galaxy structure, starting from really the basic statistics like two-point correlations up to some kind of the statistics, and also either joining this with other probes or individually we can measure different cosmological parameters. In particular, we have access to matter density, both baryonic and dark. We can say something about the cosmological constants from the galaxy structure as well. And finally, from specific ways of using the galaxy structure, like measuring the baryonic acoustic oscillations, we can measure the expansion rate at different redshifts to Hubble constant and Hubble parameter. And here are examples from final SDSS BOSS results from a few years ago. This is the curvature of the universe in this dimensionless omega k parameter. So 0 means flat space. And on the y-axis, you have here, this is the dark energy equation of state. Which gives you, tells you how the pressure and density of dark energy are related. -1 means cosmological constant. And H0 is the Hubble constant. You see that already from you can combine very well, for instance, the Planck results, which give you some constraints on that, with galaxy structure BAO, and FS is here shortcut for full shape of the power spectrum of the SDSS BOSS. You see that really some of the contours really shrink when you combine CMB with galaxy structure, but you can have some plots in some other dimensions of the cosmological parameters when you can use just the galaxy structure of the galaxy surface. So this is the motivation. I think I will move this. This is one of the motivations, but I will stop at that today in terms of motivation. You will hear much more, I think, in the other lectures. But I will start with some historical overview. And excuses to those who here know better than me. I'm not a science historian, but I try to dig out some facts and try to get them together. And also, due to brevity, I may miss some of the facts. I'm happy to be corrected, just in case. I tried to compile some kind of starting from what we would now think of prehistory of astronomy regarding the last structure of the universe. So I think really what this really started with, or who this started with, were these people. Famous Charles Messier, who was interested in comets, and he was annoyed, you can say so, about some other nebulous objects on the sky, so he decided to catalog all the objects which don't move, which are not comets, and this way he cataloged lots of what we call now galaxies. Yeah? So the final Messier catalog was one of 3 objects, which were nebulous in some way. In the southern sky, from what I found, the Lacaille was charting, doing something similar. And then there were the father and son, William and John Herschel. William, of course, is very famous for many things, but also they were also looking at the sky and charting or cataloging. Using some really huge telescopes like this one, they were charting the sky, and the end product, which was I think already after John Herschel's death, was a new general catalog, which includes lots of galaxies. If you go, for instance, to Aladdin or something, you will look for your favorite large galaxies. Many of them will have NGC something. So they were cataloged quite a while. And together with this, there was a debate which ended only in the early 20th century. What this nebulae really were. So before the term galaxy was coined, there was the term nebulae, and in the 19th century, already it was clear that there are different types of nebulae. That some of them are really clustered stars. Some of them were called planetary nebulae, and we know in astronomy we have this tendency to misknow things, or do things other, inversely than we should, like magnitudes or inverse, etc. Planetary nebulae, of course, have nothing to do with planets. Oh, okay, there might be some planets around the stars where this planetary nebula were formed, but they are not anything related to planets. But the important thing is that in addition to those, people were seeing also, these are some sketches from the American Cyclopedia, very famous somewhere on the net. So clearly, this will remind you of something well known today. A bit earlier, already Kant speculated about something which we call island universes. Maybe there were some speculations. Maybe these nebula are also some kind of like universes. And finally, Herschel already noticed already in the mid 19th century that some of these nebulae are not really distributed on the sky in the same way as stars. Now we know that this is because this is of the last structure, which is not correlated with our galaxy, because stars in our galaxy are mostly in the disk. And for instance, but in the various constellations, there are lots of these nebulae. And you can really see it if you look here at the general catalog, which was before the new general catalog, which was started by John Herschel and finished by John Herschel. And you see, this is our Milky Way. And here you have this, the nebulae which are roughly sketched around in some quadrants. They have some tendency to be distributed differently than stars. Now, as I said, this is obvious for us. This is because we see the local structure here. But it's not interesting to know that already like mid 19th century we saw this, we didn't realize as humanity what this is. And this was really until early 20th century that this was like that. There was a famous great debate, which from what I know didn't lead to any result. People didn't have observational data back then. But before the great debate happened, Weston's Slipher, which was is not always very well covered in textbooks, since 1913 said, okay, use one of the quite new inventions, the spectrograph, and I will just put it on the nebulae. I will see what happens. And what he saw is that the spiral nebulae, those which were not clear what they were, most of them had recession velocity, so they were escaping from us and with really large velocity. And I think in one of his papers already there were some speculations that this can't really be belonging to the same system as our sun, because they would disperse quite fast. They were much faster than most of the stars, actually all of the stars. And I think there was something that we now would interpret as the Hubble law mentioned, but not written down in one of the Slipher's papers. He was kind of after that already. Then in 1917, 1930s, and Lundmark, I guess some others as well, were trying to estimate the distance to M31, because it was not clear again. M31 is within our star system, which we now call the Milky Way or the galaxy. They had some estimates which already were hinting this is outside. Then there was the great debate. Interestingly, Harold Shapley, after whom the Shapley supercluster is called, was in favor of the spirals being in the Milky Way. Curtis was in favor of being outside. He had some results like that, that was quite clear. And then soon after that, the observational data settled the debate. Hubble had an idea how to estimate distances to nebulae using, for instance, nova, etc., and Cepheids, and he had some estimates of 100 kiloparsecs from us for Andromeda, which was quite clear that this cannot be the same star system as our galaxy. Finally, a few years later, when he, together with Humason, was measuring the redshift, the velocity, they discovered the Hubble law. Well, Hubble is honored for that. Although Lemaitre also in his paper has his paper, which was independently written, also so the same. And this is the famous figure from that paper, which first of all has distances and not the velocities here on this axis. There's no error bars. Finally, this fit was kind of by eye, from what I know. And not to mention that the distances were almost wrong because they were mixing different stars. So anyway, the thing is that today it looks much better, but yeah, there is the Hubble law. So the universe is not only much larger than our system, but also is expanding. I will speak about the distances and redshifts next week a bit, so I will not cover this more in this lecture, but I will move on to a bit some history closer to us. So once people already kind of agreed that there are other called galaxies, they were, I think they were called nebulae until quite late. I don't know exactly until when, but in some of the papers, Hubble's one of the famous papers is the realm of the nebulae, so they were called like that. But anyway, people still understood that these spiral nebulae and some elliptical ones are outside of our galaxy. There are other galaxies, but then there was a discussion how they are distributed, because of course there was no theory of the gravitational instability or anything which would be related to large structures, so there was room for much speculation. First of all, people noticed that the galaxies are often in some kind of clusters. So as stars in our Milky Way outside of the disk are also often in clusters, the galaxies are also in clusters. So Zwicky not only saw that, but he even was the I think the first one who kind of coined the term dark matter. He saw that the coma cluster, the dispersion, relative dispersion of galaxies is much larger than what mass inferred from the light would allow for the cluster to be stable. So he was not only discussing that clusters exist, but also that they even use them for cosmology. There was also George Abel later who classified those, identified clusters. In the 50s, the Vauquelin came with something which was very controversial back then, I believe. Which now is not such a problem for us once we know that there are filaments and walls in the universe, because he saw that this is I think from one of his papers, that the galaxies close to the Milky Way are in some flattened structure which we call the super galaxy, which he estimated some 30 megaparsec in extent. From what I know, it was not really well received until much later. Finally, the real surveys started with LEED Observatory based on photographic plates. So for those of you, well, most of you are young enough not to maybe not know well. Before we had about this, before we had CCTVs, which now we have in our mobile phones. People used photographs. I don't know if you guys know what photographs are. We had cameras in which, home usage, we had like there was film and there was some photographic emulsion that you had to. The photons were hitting, etc. You use the same for astronomy, so you put in the focal plane, you put a large glass plate with the emulsion, and then you would just gather light, and you use that later. This was in the 60s, so actually the started much earlier. You of course didn't have computers to process the data. Actually, people were drawing these things. Yes, people really meticulously taking the photographic plates and drawing based on them what they saw. Anyway, based on these photographic plates, there was the first kind of large structure catalog, LEED Observatory catalog, which had over 1 million nebulae or galaxies with positions on the sky, quite well measured already, because these are not so difficult to get even from photography plates, and fluxes, which are a bit worse. There are different issues, but there was some information, and actually this catalog was used, and some of them was also made here in Krakow, because there was some issues from Jagiellonian, from what I know. These kind of catalogs were used in the 70s by Peebles when he was developing the theory of correlation, 2-point and 3-point correlations. There is a series of papers which are a must read for everyone who wants to ever work with galaxy correlations and things like that. Peebles and some of his collaborators, and he did use those catalogs to try to measure, for instance, discover actually that the correlation function is a power law to the good approximation. So these were the first two-dimensional maps, and this is a plot from one of the papers by Shane and Britton, I think. A bit later, the discovery came of the cosmic voids and the sponge-like structure of the universe, as I like to call it. Well, we have the term cosmic web, but it depends what spiders you are used to. I mean, in Poland, we have these spiders. Well, normally, if you go to the forest or to the park, you will see usually these spiders which make these flat webs. Yeah? And cosmic web is more the type of web that some of these spiders make, that they are like 3D structure. So it's a bit like a sponge or something like that, foam. Anyway, this came from different people, Jan Nasto, Gregory and Thompson. Also, in the beginning, there was some controversy because people were discussing whether it's some selection effects. You don't see galaxies in some areas, but you see in some others. But now we know this is real. And theory followed quite soon in the early 80s. But technological advancements allowed us to go further and allowed us to go into real 3D surveys. So this was really the start of 3D surveys, because people were measuring redshifts and position on the sky. But you really need some advancements, like the ability to measure lots of redshifts at the same time, which we know with, for instance, multi-fiber spectrographs. So just to remind you why the redshift is so important in cosmology, because at the field level, you forget any perturbations together, because this is just measuring distance. Of course, the local universe is so large. Redshift doesn't follow it any longer, but redshift is a very good proxy for distance. And if you for instance, some favorite number for the Hubble constant, which you can guess from this here, then you will have the direct relation. Now, so if you are able already from even photographic plates measure the position and the flux of the galaxy, and then you can add the redshift to that, then you have lots of already information about the relative structure. And this here are some examples of how people usually plot what they see. First of all, there is the cone plot, where again this is the redshift here, and this is one of the celestial coordinates, and the other is collapse. It's because you usually cover just some part of the sky. This is some sky projection in the same way as you can project the Earth in some wide or hammer or Rayleigh projection. This is what I think John Hacker called hockey bug. This was from the area where hockey is popular. That's what I heard. I don't know if it is correct, but this is one of the equator, for instance, goes around here and it collapses the cylinder into one plot. And finally, you can also just use Cartesian coordinates. For instance, supergalactic coordinates are often popular with people who work with the cosmic web. The supergalactic coordinates were made, they were designed after supergalactic plane was kind of already agreed upon. It exists, so people said that supergalactic plane is the XY plane of this, and there's the Z coordinate. So you can use this some kind of Cartesian coordinates, where you can put the observer, for instance, here or somewhere else, and you can just make such a slice where the third coordinate is collapsed in some range. And this is all useful, depends on what you want to see, yes? Because if you want to see something which happens with redshift, these are probably more useful. If you want to see some neighborhood or something, this is useful. If you want to just see the full sky or some part of the sky, then this is useful. For instance, to compare it with CMB or something else. Of course, this is also done quantitatively, that you can, for instance, decompose it into, you can pixelize the distribution, you can decompose it in spherical harmonics, you can measure the power spectrum, etc. So these are just visualization tools, of course. The last surveys really were really revolutionizing our knowledge of the universe, starting from the 80s. And one of the famous surveys was CFA2 survey from Harvard, where mainly 3 people back then were Valérie Delaparent, Margaret Geller, and John Hakra. And there is this famous picture of so-called the stickman, which is basically direct manifestations of what we call redshift space distortion. The fact that because in a galaxy cluster, the peculiar velocities, so these which are atop of the Hubble flow of the uniform expansion, they are so large that clusters in redshift coordinates really get stretched along what we call fingers of God also. Because basically you observe galaxies which are really not at a very different distances than what you would infer from redshift, because you have added very large peculiar velocities, and this is one of these direct manifestations. But also there are some hints of, for instance, walls here, which also you have to remember that walls are also, on the other hand, more collapsed in redshift space because of the so-called Kaiser effect, which is a squashing effect on large sticks. Anyway. Now let's move on a bit to some bigger picture. So after the success of the first surveys and also first simulation, which were consistent with this distribution that we see on the sky, at least in some models, people realized that you have to really do better, to really make massive surveys, plan surveys on very large chunks of the sky. And extremely successful, and so far until now the most successful has been SDSS, which started in 2000. Which the idea was the following: we want to have not only some chunks of the sky, some random, but okay, we have some kind of telescopes that we measure something here, there. No, we even want to have a telescope devoted to just that, to measure a large part of the sky, to make representative samples, because we don't want to hear it on just one cluster, on just one void, which doesn't tell us enough about the universe. We have to measure the large structures at different reshifts to different parts of the sky. So large areas of the sky and reaching as far from us as possible. Ideally, we want to the full sky and to any redshift possible, which of course is not doable even with incoming surveys like Euclid, because you still have to choose some whatever yourself. And as I say, until now, this will be obsolete in a few months, I think. The most has been Sloan, digital sky survey, which started in, I think, early 2000 or something a bit before, which had a dedicated, first of all, a telescope for dedicated photometric observations. So it made its own target catalog, and then a telescope, or even more than one, I think, for spectroscopy, for redshift of galaxies, of quasars, but also later stars. And it gathered in the final release of stage 4, some 4 million spectra, some 25% of the sky. But already now, I will mention this later, there's DESI, which hasn't published the data, but already DESI has more depth from so-called science validation space. So this is another era. But anyway, still, even in DESI, and even in Euclid, which really cover lots of the sky and go very deep, you still have to make a trade-off between how much you can cover and how deep you can reach. Because you cannot really practically measure spectrum of every single galaxy that is there. Because there are, as I mentioned, some 10, 11 galaxies in the observable universe. There is no way, especially for the faint galaxies, you have to integrate a long time to get, because you don't need, you need a redshift, you need to identify some lines, you need to integrate for sufficiently long time. So the 3D galaxy distribution to be observed, this is expensive and time-consuming. Expensive also in terms of money, because either you have to invest into a dedicated instrument, or you have to use time on some other instruments that are needed for some other astronomical research as well. Okay. So generally, I mentioned already this, that SDSS joined these two approaches. There are two main approaches that I survey the extragalactic state. Because I'm talking about the extragalactic state here, of course. I'm not covering the star surveys, which are similar, but they have different goals, etc. So the first approach, which really was existed back in the photographic plate time, is just a photometric. You just make pictures of the universe, just image the sky at different parts and different wavelengths. And here you can do it also in outside of the optical domain. You still think that you can say that radio continuum surveys are kind of imaging surveys as well. And you can do it anywhere on the sky because you don't need to know anything a priori. Well, you probably need to avoid our galaxy, Magellan cloud. There you will have saturation if you want to integrate a long time. But if you go outside areas where you know there are lots of galaxy, Milky Way stars, you can get some very nice pictures of where most of these are galaxies. And there was a press release from James Wood, I understand the American president led or something like that. It's really amazing for me that you get politicians of such high rank. But anyway, there was a picture from James Webb of one of the big fields where, again, there was this very big field of just galaxies and just a few stars. And secondly, as I said already, spectroscopic is where you want to get the spectra. First of all, the redshift. So you really need to identify either some pair of lines or some emission line that you trust to get this redshift. But you can also be under the spectra and want to know more about galaxies themselves. But the thing, if you use except to use prism or whatever kind of like Euclid fields, for instance, or Hubble also had, and also Primus and some other surveys, you normally need to know where to put your endings of your fibers. So you have the fiber optics which go to the spectrograms, but they have some endings, and you have to put them on a galaxy. So usually you need so-called targets. For SDSS, this was that case. For this is the case. This will be the case for formals. So most of the deep and wide-angle redshift surveys need to know where the targets are. So they usually need this photometric part first. So some use their own measurements like SDSS, but some use some other measurements from other surveys to have this. And finally, this is more recent because you also need technological advantages also in storing the data. You can now do it also, repeat this to get time variations because you have supernovae, because you have some quasars are also variable, and some other objects are variable. So in the radio domain, you have, for instance, radio bursts, etc. Yes? So now you can join all those both to get time variations of the objects as well. And as I mentioned already, we use CCDs for that and store this in digital form, obviously. And the data set would vary from 10 to the 3, depends if you have some smaller, deep, but very targeted surveys. For instance, in the Cosmos, there is a small field Cosmos, just called like Cosmos. There are lots of surveys there, and some of them just will have a few thousand objects, for instance, with very high redshift, because they target some specific objects. But then, especially if you go to the photometric part, typical the surveys they will have up to 10 to 9 sources. I think Y is 2 billion already, and this keeps growing. In the era of Euclid and LSST, this will be much larger. This is expected to grow by 10 or more. Instead, we go on without any break.
Unless you want it.
So usually it's 1 hour or?
Yes.
So until 6. Okay.
If you want to have it for
We'll see. Okay. I can leave some for the other version. Okay, now I will just go very quickly over a few surveys, this is a subject selection. There is no way to cover all the important surveys that happened. So I will go in a bit historical order, but also about mostly focusing on really wide angle and important surveys that without really showing results from them. This is another story, it's probably a different lecture, but just to tell you about what these surveys were. I spoke a lot about Sloan, but a very important survey, more or less at the same time when Sloan started, was 2DF, Two Degree Field Galaxy Redshift Survey. The name came from the fact that it covers 2 degree on the sky, the observations. This was done in Australia by a team mostly of British and Australian astronomers. Really important survey, which not only really nicely showed the stellar structure. This observations here. You see really the walls and filaments and also clusters. But also it was used for really first very good quantitative measurements from the Raster structure, such as estimates of the matter density of the universe, which were totally inconsistent with the popular model until before CMB happened with the Einstein deciphering universe. So a universe which is flat but has omega matrix 1. 2DF showed that you cannot really correlations that you measure from the Raster structure really are not consistent with this unless you come with some very exotic ideas. And also 2DF was together with Sloan, I think it was really the same year, was the first one to measure the baryon acoustic oscillations in the large-scale structure. So a signal which comes from the early universe, which is due to the processes which were happening before the recombination, sound waves propagating in the CMB that are now kind of they left a pattern in the elastic structure that you can measure and use for instance, Hubble constant and Hubble parameter measurements. So this was a very important survey, and really there were some really very important results from that. Even if from today's standard it was really shallow, redshift 0.2, not that many galaxies, 100,000 is more than 1 order of magnitude smaller than SDSS, and just 4% of the sky on the equator and in the southern sky. A bit before, but also more or less at the same time, people also started doing real surveys from the sky, from space. This is because our atmosphere has gives us very nice clouds that you can watch and other things like rainbow, etc. But first, it's a huge problem, not only because of cloud, because of rain, but also because of vapor and because of many other finally the so-called seeing that doesn't allow you to go down in the resolution to extremely small numbers. So some wavelengths basically cannot be observed from the ground. For instance, the emitting at far infrared, except for some windows in the mid-infrared, I think you cannot observe these from the ground. So you have to send telescope to space to observe them. And one of the first ones, which I think this was the first one which gave kind of all-sky survey, was IRIS, which operated in the 80s and gave a catalog of mid-infrared sources, which outside of here the Milky Way were most galaxies. There was a catalog of infrared sources which were in a large galaxies. And based on IRIS, the first all-sky redshift survey was made. People took these infrared sources for which they only had fluxes, infrared fluxes, and used a different telescope to measure the redshift from them. And this is the result of the PSCZ survey. Like the publication of that was only in 2000, although the survey kind of existed a little bit before, and lots of science was done with it. And here also, for example, you see some hints of the supergalactic plane, even if this is not a very dense survey, just 15,000 redshift. So on average, more less than 1 galaxy per square degree in the sky, but still very useful information. And this was the first really 3D map of the entire, almost entire galactic sky. These areas are not covered because of the Milky Way, and this because some observational, with the strong observational effects from that telescope. but didn't chart these areas. A bit later, people said that let's try also with from the ground, but a bit in wavelengths that can be observed from the ground, which is the near infrared, from between 1 and 2.5 microns. And these are very interesting and useful wavelengths for two reasons. First of all, because we have this lag that our atmosphere has windows in this, so there are a few bands that you can observe from the ground. But secondly, these bands are really, at least in the local universe, tracing the stellar mass of galaxies very well. This is because most of the mass of galaxies is dominated by reddish stars. Yes? So either all red stars or kind of K, so lighter than the sun. And if you observe galaxies in these wavelengths, in the local universe, you really observe the light distribution and the mass, the baryon mass distribution, not necessarily the dark matter mass distribution, but the baryon mass distribution. So this is why this two-mass survey is very useful, and it really gives beautiful pictures, even if you, as I already showed earlier, you don't say anything about any distance of any galaxy. You can clearly see the cosmic wave in such a plot. Of course, this is because this is the projection of not a very wide range of projections. You don't collapse the construction on top of each other, but still, I think this is quite impressive that if you don't say anything about that, you don't say that this one galaxy is farther away than another, you can clearly see the cosmic waves, you see the filaments and superclusters, etc. And this was done by two identical telescopes because it was a ground-based survey. So one was in Arizona and the other was in Chile, and 3 infrared bands, and charted some 1 million galaxies. There are a bit more than 2 months, but the final 1.6 million galaxies. And of course, lots of stars, and more than that. What here are stars from our Milky Way. Okay. As I said, the largest, and if I give a lecture about this anytime in the coming in the next few months, I will have to change this slide. But until now, as we are standing in terms of what is published, and what is related to astronomers in the general public, the largest survey that exists is SDSS, Long Digital Sky Survey, which has now gone to the 5th stage, and every stage has releases. So there were 17 data releases up to the 4th stage. It covered some 35% of the sky, but 25% is in spectroscopy. Had targets pre-selected from their own SDSS photometry, but also used later some extra photometry, for instance, from mid-infrared WISE. And in the 17th data release, there are some 3 million galaxies and 1 million quasars targeted in different ways. So there is a so-called flux limited part, and there are colors selected to select some specific galaxies or quasars. Plus, there is also a catalog from SDSS, which includes some 200 million extragalactic sources in photometry. Yeah? So just fluxes, 5 bands. But as I said, there's more than that. But it's not available publicly yet. Now, if you think about what is the deepest in terms of a full sky survey, it doesn't matter redshift or not redshift survey. Until now, in terms of extragalactic sky, the largest is coming from the WISE telescope, and this is not the most recent map from there. This is a telescope, I think it's still Super 18. Which started in 4 infrared bands from 3.5 micron to 25 micron, so very similar to Spitzer, actually on purpose, designed like that. And then after the coolant, there was a coolant to measuring the 12 and 23 microns. When the coolant went off, only the first 2 bands, 3.5 and 4.6 microns, were measured. It is orbiting the Earth, so it has a specific pattern. Actually, this, for instance, what you see here is because of some issues that there was some coolant not there anymore, some problems with observation. So this is a pattern it's on an elliptical orbit. Yes, so it goes around the ecliptical orbit. Yes, so it goes around the ecliptic poles, and that's why you have missing data there. There have been a lot of releases. This is from almost 10 years ago, from so-called all-wise catalog, when there were like 700 million objects. Now the most recent release has already 1.9 billion sources. Of course, not all of these are galaxies, but a large fraction of these are. Except of course all these which are stars, are actually even saturation stars are not really resolved here, because the resolution is 6 arc seconds for this survey. Anyway, this is the photometric survey. There are no registers here. Although people have used this survey, including myself, with other catalogs to get registers. If you want to know more, these are this is net price and the most recent catalog called Catwise is this one. This data actually is publicly available from IPAC. Although I must admit that getting this on your list is quite a hassle if you want to get the whole catalog. I did it with this one. It took me quite a while, and it's quite a feat, but well. All right. Now, if you now think about, now we are going a bit back in the historical times. What is the largest catalog in terms of the optical bands? The thing, in terms of the all sky catalog covers the full 4 pi radians, and optical bands like BR. It turns out that until now, except for Gaia, Gaia doesn't really measure galaxies. The largest catalog that exists is based on all good or not good photographic plates. So there were two surveys. There was COS2 in the south, and in the north there was I forgot the name. But there were two surveys in the south and in the north that measured the sky in BRI bands. I is for like infrared. And this was lying somewhere in the archives. People, first of all, digitized this plate. So they really scanned the machine in Edinburgh and digitized the catalog. So they took the photographic plates, scanned them, and made a digital catalog, photometric catalog, so to say. And later, much later, led by John Peacock, there was an effort to make a galaxy catalog of it. So basically extract catalog, extragalactic sources. So out of 2 billion sources, there are some 10% scientifically useful, and actually you can use. This has been, for instance, this catalog was used for target selection in 2DF, because 2DF started when there were no photometric catalogs covering these areas where the ratios were measured. So this was used to select galactic targets, extragalactic targets there. So from what I know, well, there will be probably finally all sky catalog in optical covering the which will overcome this one, but until now, if you want to plot the full 4 pi radians of extragalactic sky in the optical, you have to use this catalog, unless you want to do some other catalogs. And finally, the largest uniform all sky redshift sample. So all these names are needed here because, of course, there are larger all-sky redshift samples if you blew different samples like SDSS and others, which are deeper in samples of the sky and shallower in others. But if you want to have a uniformly selected, this one is flux limited in the near infrared 2 microns K band. So in terms of such uniformly selected redshift surveys, the largest one is still Thomas redshift survey. So this was based on the Thomas photometric catalog in the infrared, and a huge effort started by John Hakra, who didn't manage to see this completed because he died in 2011. Was to measure a uniform sample of galaxies from Thomas, and this was not done with a single telescope. This was done gathering already existing redshifts from other catalogs, and then okay, we need a redshift on this galaxy, we get time for somewhere. And they were people, authors of these papers, we did it like that, really getting redshifts from different telescopes to get this, but there is a beautiful very low redshift structure, which in this plot by Tom Jarrett is well described. And if you go to Tom Jarrett's webpage, you can see this very nice picture of many known structures in the local universe. Okay. And finally, about DESI, I cannot show the sky distribution of galaxies from the DESI because it's not public and I'm not a member of DESI. And even if I were, I wouldn't be allowed to do this because it's not yet released. But before DESI, the spectroscopic catalog happened, there was the DESI legacy imaging surveys that they were also conglomerated a few surveys in GRZ bands, which joined from different telescopes. People joined a large fraction of the sky. This is the depth between 20 and 25. You see that the different areas of the sky have different depth, but this is uniformized in some way to get some uniform catalog, and this is the largest digital optical catalog that exists. So not digitized photographic plates, but really starting from digital CCD information. And this is used for cosmology, and I believe that because John Peacock will discuss some CMB cross correlation with galaxy structure, and his group used this catalog for some of these. So you might hear about this more. But so this is not only used for cosmology on its own, but it's most importantly used for targets for DESI spectroscopic measurements, but also for plant formats in which some of me and some of my colleagues are taking part. We also are using DESI for DESI legacy imaging surveys. Legacy surveys that are called for targets. And there are different catalogs made based on this by many people. And in general, there are some 50 million galaxies in this legacy surveys catalog. And finally, something that you will certainly hear about if you follow any news in astronomy in a few months, I think from now. I don't know when exactly this will be happening, but DESI is really a new era of redshift survey because the instrument is so fast that it can measure redshift very quickly, much quicker than many other instruments. And this allows to have a very ambitious and fast program measuring redshift that will really change the perspective that SDSS will be totally dwarfed, because this will give you 1 order of magnitude more redshift than SDSS gave. And already the interesting thing is that in what is called survey validation data, which you would normally think is, and it is really a subset of what will be there. There are more redshifts already than all the previous redshift surveys. So everything that I spoke so far is dwarfed by already science validation, survey validation of this survey. So we can also expect that cosmology from the survey will be really revolutionary in a sense that the statistical errors will go down, and then actually things may be getting interesting because any tension that we see so already can be more pronounced, because if your statistics is better and your statistical error goes down, then your systematic errors start to matter much more. And I expect we should expect unexpected things from this kind of service. This will be the idea is quite similar to SDSS in a sense that there is a galaxy selection, so flux limited galaxy sample deeper than color selected galaxies, so for instance luminous red galaxies, other galaxies, quasars at different redshift, selected from these legacy surveys, and then you measure redshift for them to get some level. And I think this is from the press release of DESI from earlier this year, and I believe these are this is part of the science validation data, but this is so secret until now that they didn't even put the redshift, the redshift coordinate here. Well, okay, but I understand that this is because the science measurements will come at some point this year, and they don't want to spoil the fun, let it go. So I heard in a recent conference that the science results should be late this year from the science of survey validation data. The full data will come till 2026 or so. Okay, so how much do we have? Right. Okay, so now a few slides from that I borrowed from John Peacock from one of his lectures a few years back, where he really nicely gathered the year in linear scaling and logarithmic scaling the amount of redshifts that we have for galaxies. So starting from early days, from Cypher, you had some very abrupt race in Cypher, Himason, and others, yes, who continued until even 50s in getting redshifts. So first he measured redshifts for Hubble, then also with Mayol, Sandwich, and others in 50s, but it was a bit flattened. Then there was the revised Shapley Ames catalog, so we are already in 1980s. And this is when the era of last survey started. You see the slope now changes with CFA. Then 2DF, the slope goes up again. In between there was Las Campanas redshift survey, which for various reasons was a very interesting survey, but for various reasons was not that revolutionary for science, for cosmological studies. Then as they said, this is certainly not the full data release, the final data release here, so I think there might be a bit more. And then if we go into near future and a bit far future, about Euclid, we will hear from Hank Hoekstra, I think starting from tomorrow. You see that the slope should go up again. And here is the Hubble alternative field. For now, maybe we should put the James Webb alternative field or whatever it is called somewhere there. This is the goal, which I don't think we will ever reach. If you see what is the power the number comes here. Yes, I guess well, we could dream about this slope to reach here, but this is really my goal because we will have. I think there will be more interesting things to do in the era of Des in Euclid with tensions that can appear, or at least some things that some gaps in our theoretical understanding that we have to fill in first before we go for even larger surface. Well, of course, this is always possible. Okay. So just to in a few remaining slides, I just have at the end some short discussion about which will be some introduction into the next lecture that I will have next week. But I focused, of course, on the optical infrared and these domains because this is what is the most interesting for galaxy. If you want to study regular galaxies and galaxy structure, if you want to study light that traces the mass really well, the dark matter especially, you have to go into optical and infrared because these are thermal processes, etc. And also we quite well understand what is happening there. But the sky is charted in many other wavelengths, actually any wavelengths from gamma to the longest radio. And I would say that in some aspects, the radio mapping of the last structure is really the future. If the SKA survey doesn't have any problems, if it comes in time, it should be in a few years from now already. And if we manage to process the data and understand them, this will be really a real revolution in several years from now, our understanding. But until this happens, we still have quite a bit of surveys that map the last structure. Starting from, for instance, already quite ancient, I would say, NVSF, which was on VLA, which was first such large survey in the radio continuum at 1.4 gigahertz in the wavelength related to hydrogen transition. That was what we would call in the optical imaging survey, the continuum survey. Basically, just you have sources and you have fluxes for them, radio fluxes, and you don't have much more. So this is some plot from one of the papers. You don't see any elastic structure here also because how it is plotted, but you wouldn't see any elastic structure because most of these sources are quasars or AGN and they are distributed on a very large distance, and any elastic structure is really diluted or can collapse if you want to plot it. So it's not very well, not very good way to show the large scale structure, but you do observe galaxies at different redshifts there. And these days we have also people also went to lower frequencies, so longer wavelengths. And a very successful survey which is ongoing is LOFAR, low frequency array, which is a European array of telescopes, including also in Poland, but mostly in the Netherlands. And in terms of for some cosmological extragalactic studies, the most important so far has been one of the surveys, 2-meter sky survey from there, which had 2 data releases, and this is the picture where on the sky in equatorial coordinates this second data release is. This is the first data release, the second. There are some 4.4 million sources there, and already this is the largest radio survey that has been made in terms of the number of sources, and even if it just covers a fraction of the sky. And in fact, all these dots here are pointing to LOFAR, so this is all that LOFAR will measure, and the goal is to have the full northern sky measured with this telescope with really good resolutions for radio, because with radio it is so easy to get to low resolution with continuous surveys. And again, this is not a redshift survey, but similarly as with shorter wavelengths, these are mostly quasars and AGNs, larger, but because in the radio there is this specific thing that if you go to lower fluxes, you start seeing more local star-forming galaxies. This is because radio wavelengths are not emitted in thermal processes, but due to acceleration of electrons, and then the flux of the galaxy is not very well correlated with this distance. You can have a very distant quasar which will be bright in the radio as we measure it, but very faint in the optical. And if you want to see local galaxies, there is some paradox that you really have to go to low fluxes in radio to start seeing them, and lots already start seeing them. You already have this, the distribution in terms of redshift is higher redshift AGNs and lower redshift star-forming galaxies. So this is really interesting so far for mostly galaxy evolution, but it will be interesting for cosmology as well. And this is a comparison of what is happening or what is planned in terms of the radio surveys. All these gray are those which already exist. So different acronyms of different surveys to look up. This is the frequency at which you observe the sources. This is the sensitivity, or flux limit, so to say, and the sizes of these are the resolution of the instrument or the observations. Yeah? So that you want to be down here. You want to have the smallest possible circles, the best possible resolution. And you see that today's surveys, like these are LOFAR surveys. These first ones go down here, so they go to lower sensitivity. And this is Apertive is another survey on maybe from the Netherlands. EMU is an SK precursor being done in Australia, which there is some early data there. And there will be some larger data coming up in a few years. So you see that this is really improving all various aspects. And you can imagine that if you enlarge these samples and you have much better resolution, use much better sensitivity, you start to learn more and more about not only individual radio galaxies, but about generally large scale structure that you can infer from them. Just to clarify here again, these are so-called continuum surveys, where you basically measure, you can call it an image of a galaxy. Yes? You measure light distribution of a source, and for instance, often it's like double lobes and things like that. You know nothing about the redshift from these observations alone. Kind of redshift surveys from radio are also possible. They were done, for instance, with the already dead galaxy more. Alpha, you can basically measure the H1 line, and there by measuring in different channels, you basically observe either you detect the galaxy or not in this line. If you detect it, then you know the redshift, because you just go from redshift 0 maybe H1 line to redshift it more and more, and then you want to, when you detect a galaxy, this position in this redshift, then you have this redshift. It is possible that there are plans also under escape precautions. I think ASCAP will do it. Yes, ASCAP, and then in South Africa also one of the surveys might, I think, or some other is also doing that. This is much more expensive and time consuming, as in the optical for different reasons. But they will be there. There will be large redshift surveys, so to say, from the radio as well, sooner or later. And finally, just a few maps that we do also make in other wavelengths. Not always due to interest in terms of cosmology from these, but more due to interest in exotic processes. Especially if you send a satellite to space, then you can measure the full sky much more easily than from the ground, because you don't have to have, for instance, two telescopes in two different parts of the Earth. And this is done in many wavelengths: UV, X-ray, gamma ray, infrared bands, which are not available from the ground, likewise. So Akari has lots of wavelengths, and you get different mass, which again usually are dominated by our galaxy. But for instance, Fermi has a really nice data set, both resolved extragalactic sources, mostly blazars, some other quasars, but also there's the extragalactic Fermi background, X-ray background, which is also has some cosmological information. So these various wavelengths depends on how good resolution you can get, how sensitive you can get. For instance, Galax was not very useful for cosmology, more for galaxy evolution, because it was very, as you see, non-uniform. The resolution was not very good, but you can use those for different cosmological studies. Rosa, for instance, was very good at detecting clusters, because clusters are bright in X-ray, and there are catalogs of clusters and even some information about cosmic web inferred from the Rosa cluster distribution. Okay. So this will be a few final slides about to sum up. First of all, I didn't speak about all of those. Some of those you will hear about, I think, from others in this school. If not, excuse me, and I just have to look up, because there's no way to cover everything which is happening or will be happening as planned. But just to sum up here, that in terms of surveys which already happened or are happening still, here is some short summary. So SDSS, photometry, but more important, spectroscopy. 3 surveys which are very important for weak lensing: dark energy survey, kilodegree survey, and hyperspectrum survey, which have covered not full sky. They don't have this ambition, but they cover quite considerable chunks of the sky already. But they go very deep, up to magnitudes like 25, 26, and more importantly, especially for weak lens observations, has very stable photometries. The telescopes, the cameras are designed in such a way to guarantee very good, stable observations, so they can measure, go down to very small angular scales below 1 arcsecond, together with some other optics, for instance, and they do it in the optical and near infrared. So these are really very important surveys. And DESI coming up, which I mentioned, and many others. And from what I was able to kind of count, this all give you, let's say, terabytes of data. I mean, okay, if you gather them all together, maybe this will be large terabytes. Still, this is in the terabytes version. Now, what is coming up, you will hear about these from HEC, I think, from Hoekstra, and LSSD. This will be, together with an SPA, will be into petabyte regime easily. So in terms of number of galaxies, this will be not anymore in millions, but in billions probably. So Euclid will be a space telescope, which I don't know when it will be launched, because there are some issues. It was supposed to be launched on Soyuz rockets. You can imagine it's not doable these days. So I don't know what will be the solution, but there are some like after 23. I'm not in Euclid, so I don't know. But what it will do, it will do deep photometry and slitless spectroscopy. So there will be spectroscopy, but there will be just rainbows on the sky from which you have to get redshifts. So near infrared, very very important. So this will be something you cannot do from 0.2 arc-second resolution, very deep, and lots of redshifts and very good photometry. LSST, on the other hand, very large telescope dedicated to surveys, 10-year survey, which is expected to have, I heard, 4 billion sources in terms of extra. What will be the number, I don't know. The telescope is being built, and there are, of course, delays. There are always some delays, but it's kind of going well. So we should expect some data in a few years from now from the system for sure. So again, large structure, weak lensing, and this type of stuff for sure. And finally, SKA is a very ambitious plan, approved already by many governments. This is a kind of very international plan because the budget is some 1 billion euro, I think, or something like that. This observatory. Arrays of radio telescopes in South Africa and in Australia in different wavelengths, so shorter and longer wavelengths, and both continuous surveys, but also H1, which I mentioned, so kind of redshift surveys. When it will start, I don't know. The numbers, usually people speak about mid-2020s, but we're already into 2022, so I don't know if this is realistic. But there are precursors built and operating. Results from them are coming, Meerkat in South Africa, and then in Australia. And especially about SKA, what I hear is that you really need some progress in technology because the amount of data will be so large that you cannot really process them with today's tools. And even with LSST, there will be no way really to download LSST data like that. I mean, because the data will be so large because this will be a 10-year, every night a large part of the sky will be measured. So you will have so many data that you can get the data if you bring your own disks, for instance, to Chile or something. But you cannot really just get them on the internet because they will be just large. So there will be specific ways of pre-processing them for the community. And SK certainly, I don't know with Euclid, but it might be the same problem. Well, with Euclid, the problem might be also that you have to first send the data from space, which is a limit, like in Gaia, for instance. You cannot really send all the data. Okay, so just to not to keep you too long, all that is basically kind of data avalanche in modern astronomy that leads to some problems that we have to solve. Here are some numbers that I think I got from my colleague Paula Solarz. Some of the surveys. There is one which I didn't really mention because it's not really very. It has galactic sources, but not very good for large structure. Zwicky transient facility, which has some petabytes of emerging data, etc. And as I say, you cannot not only process this data with your own tools. Not only to store them in your desktop or even some survey that you may have somewhere in your group, but you cannot often anymore even transfer them from the. I mean, 30 terabytes per night. If you want to have 10 years of observations, as I say, you really can just go somewhere and send it by FTP. So this is already happening with the transfer with Gaia, because you might know that Gaia in principle observes galaxies, but because their decisions have to be made that Gaia is a star, for stars from our Milky Way, which also observes quasars, by the way, but basically point source the survey. It has inbuilt filtering on board that sends really only the point sources to the ground, the information about point sources. The extended sources are not really stored. They are measured, they are measured by Gaia, but they are not, you don't get information about them. So with this, you can have similar issues. You may need some decision. For instance, you can, measure a specific information about some of the sources, and you will get only this information, but not everything. Like you could still do with SDSS. For instance, with SDSS, you can just go to the web page and you can really get all the spectra and all the, I think, all the imaging data very few. It's still feasible. I mean, you need quite a bit of large disks, but it's doable, but not with this new service. This leads to challenges, but also leads to some advantages because statistics are getting better, so we can do better. And just as a very short introduction to what I will partly cover in my next lecture, is that one of these challenges that we face is in measuring redshifts. I told you that I don't expect that we will measure redshift for most of the galaxies in the universe because there are too many of them for this to really do it in practical terms. And as I said, redshift is very important, actually crucial for cosmology because for large structure cosmology, because you have to know the 3D distribution. And well, this is already not valid anymore. I should release this 5 million or less together, all the surveys. This growth is growing now by 1 order of magnitude, but as I said already, in imaging surveys, we have easily 10 to 8 galaxies, but expected to have 10 to 10 from, for instance, LSST. Now, luckily, nature is not so mean to us. We can use this large amount of data, combine what we have from photometry and from spectroscopy to even estimate redshifts. This is just an example that I want to show about how you can combine these different types of information. That you can join, for instance, these different photometric catalogs, or at least if you measure different filters. Here are GIZ filters. Shown here. This is the wavelength, and this is the transmission of the filter. This lines here. These are some example spectra of galaxies. So, for instance, because galaxies together with being redshifted, you have the redshift means that the lines are shifted, or continuum is shifted, but also on average, farther galaxies are fainter. So, if you measure them in different filters, you see that the colors, so the combinations of filters, change with redshift. And this is used to our advantage that we can estimate the redshifts from photometry. And this is the link with large amount of data is there. If you want to, this works on the statistical level in the sense that if you have like 1 million galaxies, for instance, you estimate photometric redshifts for all of them. Statistically, they will be quite good in a sense that they will have some scatter which is acceptable for some goals, and also the average redshift will be correct. But this is possible in terms of statistics. If you have just 10 galaxies and you estimate photometric redshifts for them, it's unlikely that this will be correct. Yeah? You can have, it's enough to have 2 outliers, and there will be a problem. So this is a fast way by having these millions of galaxies, for instance, from LSST. This will be the only feasible way to really get redshift estimates for those numbers. But of course, there will be much worse, and that's why we use spectroscopy. Usually, the precision is worse by 2 orders of magnitude. Okay, and this is just the final slide to show an example. Just one randomly chosen catalog with photometric redshifts, which is the same tool that we saw before in black and white, but we color coded this with photometric redshifts, where again, if you just pick a single galaxy here, I cannot tell you that the redshift of it is correct, in the sense that it can be 20% smaller, 20% larger, even more if you are unlucky. But you see clearly that the Russell structure is there. If you color code with redshift starting from violet, redshift 0 to red at some point 15, some structures are really the correct redshift, like Shapley and others. You see clearly that that 3D structure is preserved. This is just an example, and this is possible thanks to this revolution, which started with catalogs like Tumas and others, that you have already, you go into millions of galaxies, you have multi-wavelength photometry, you have some sort of overlapping spectroscopy, and you can use it, and of course you can use it for cosmology and just pictures like that. So that would be all for today. Thanks.
Before your question, I'd like to add a few words to historical facts.
Sure.
My comments is related to law. 2 years before Hubble, Georges Lemaitre accused this from Einstein equations and tried to estimate the constant between velocity and distance. This paper was published in the French journal, unknown for English language scientists, because 2 years and more scientists didn't know, most scientists English speaking. In 1915, Astronomical International Union recommended to recall Hubble as Hubble Lemaitre.
Yeah.
Please.
Yeah, I agree. I led many comments, but only a few, and I avoid the part the conflict of interest. I think the review is rather important. The first one you show it, let's start from the last one. And then there is you mentioned that, but there is a very important point.
Which one?
Because the gamma ray doesn't matter, it's a distribution of gamma ray.
This one?
Yeah, this observation is very, very important. And there is a paper which came out, I guess, either this year or last year. And after you subtract all the contribution of the gamma, of the galaxy and so on, they show that the gamma background is completely explained and very clearly from the simulation picture that they might is completely explained the gamma ray background using star forming galaxies. This is a very important result. I think probably is one of the best results of the Fermi. The second one, as I said, I avoid where I have conflict of interest. The second one is when you mentioned about the strategy survey, I think it would be fair to refer also to Jinga. Jinga is, I mean, that we wouldn't have the strategy survey without G. So it did both, in fact, it did, is the one who made actually also there at the time. Then going on is a far and skip all the part of the, of course, of the part of dear friend like Margaret John Glenn, is very, we could have a long discussion on that. When you mentioned the popularity, the supercluster, yeah, I think you mentioned 30 megaparsec.
Well, that's what I found.
25 and so on. But in that part, the vocabulary, I mean, if you do history, you must do it right. And the vocabulary was completely wrong, because you cannot have a dynamical system that big, because the average time is not enough to get there. And in any case, the vocabulary was thinking about an hierarchical universe, which is, repeating and so on and so forth. So then let's go to Shapley. I mean, Shapley, we should mention all the work of Shapley. Shapley did a fantastic work. In fact, all himself used the local observation of Shapley had a bunch of gear looking at the plate to make the map of and shape it down as well. And the local the observation of the capital of Shapley's at the manuscript port is obviously, I mean, used to say the distribution of galaxies. I mean, he had not clear at the time idea, but it was very clear that the distribution of galaxies was not uniform. So, I mean, if you mention something, you should give the worst. then I don't go on the other large-scale structures because I have a cost. But it's completely low.
I mentioned Shapley just in this context here, that
Yeah, it was a theory that's like, I mean, if you do it new, you should do it right. It did a lot of work.
I didn't cover what Shapley had. In terms of popular, I just mentioned that he had this idea of super galaxy. Of course, this was not correct in the sense of one star. Yeah, but the term of the supergalactic plane stuck. And in terms of the extent, we
I mean, it was a comment in Texas, so I know that when I knew it. But it was completely off because for one thing, it thought that that was a linear method.
yes, that's true. Yes,
I mean,
yes.
and so it was wrong on that. And it was wrong on the hierarchy of the universe because I mean, we had a lot of discussion because it's not true. We all know now. So, what I mean is for students, it's good to know the truth. I mean, I stopped here. So that person is also understand. But I stopped here. Actually, you know, for instance, that Vicky was very mad with Jonathan because Vicky couldn't use the 48 Schmidt telescope. He was doing this, was a little of politics. Well, okay. Stop. You trigger too many people. Are you ready?
Okay, but then maybe not exactly a question, but a comment.
Yeah, it's a comment because I think that which is incomplete. I mean, you can see that because people don't get the wrong idea. Sorry, but I feel strong about it.
Yeah, Guido, it's very difficult to speak about history in front of someone who has lived this history. And to be fair, something which Guido left out because of the conflict of interest, the discovery of voids is also an important.
Yeah. I don't want to get to anything. I mean, I didn't.
Yes, I agree with this. But this was not meant really about voice, but more about the filamentary and complex structure.
Tell you something. That concept that time. You I didn't see it because I didn't want to participate. You wrote a book, I guess. Or no, I don't know.
I think that there was a paper.
At that time, it was a student. And Gregory actually, is Gregory the other guy?
I believe so, yes. That's what I found. I'm not
So
sure.
you don't know? Sure.
Well, that's what the pictures I found. I'm not
You
100%
mean
sure.
you put the picture, you don't know who is in the picture?
I believe that's them, yes.
You believe. And this Gregory.
Question.
That, yeah. Sorry.
So one question, like when you are showing that cone diagram, in this when I'm okay collecting the light from all the galaxies and everything. So after some time, is there a scale on which I see that okay, this or let's say the universe is homogeneous? Like when do we start to see? Is there a scale at which we start to see that okay, it is homogeneous, like the galaxy clustering or something like these?
Well, homogeneity is kind of on a larger scale than what you see on such plots, yeah? Because even in Vickers searchable one, if you see the structure and Clark's cluster and measure this cluster, this has been done. So the homogeneity is there if you make a plot that goes to a very large range, and then you kind of zoom out, and you will see homogeneous structure on very large scales. But If your redshift range is not large enough, then you don't see it.
So for large redshift range, I see.
Yeah, that's the question. We have a plot here. Oh, these are still, well, maybe okay.
It's because
This is like from a 2D equation here. And you see that here already, because these are large redshift ranges, you don't really see any more by eye clustering. Yeah.
And in these galaxies, let's say when I'm seeing these clustering, so I infer from, let's say, the dark matter. So that dark matter, when I'm inferring, which theory of gravity do I use? Because if I use Newtonian gravity, okay. But in general relativity, we have only FLRW.
Well, you can do what you want. I mean, this is the observed distribution of galaxies.
Okay, then we can.
This is the light distribution. You can measure the correlations or whatever statistics you want.
Okay.
And then you have your theory, which links this to dark matter clustering, for instance, or dark matter distribution. And the thing about lambda CDM is that we don't know of any better theory which would explain this clustering of galaxies than some composition of dark matter clustering plus galaxy bias, which can be more or less sophisticated, but still it is working. Supported by simulations which basically show the same picture. Yeah? So that's how it is done. And could you do it in other theories as well? And in particular, there are some so-called modified gravity theories, yeah, which go add something to the new Einstein equations, which in particular change the clustering pattern in some way. The growth rate structure, basically. Yeah? So you don't see it by eye, but you do sets, you have different growth rates, for instance, in these theories, and this can be also measurable from. And one of the goals of Euclid is, for instance, to do that as well, to see if clustering is consistent with lambda CDM. So cosmological constant.
Question? No question. Thank you, David.